In this video, we will be talking about the chain rule and the extended power rule, which are really the same thing. One is just a little bit more specific, but ultimately I want to focus on the chain rule itself and how to use it. In the previous video, we talked about when we need to use it. Here, let's just go ahead and talk about how it would approach. But the extended power rule is really nice to know because it gets at a lot of these questions like, what if I have a power of another function? How do I deal with it? So it extends the rule. Instead of just having the power rule just works for x to the k. What if I have f of x to the k? And that's exactly what it says here. ddx of f of x to the k. And what it says is it is equal to k times f of x to the k minus 1. And notice that's exactly the same as the normal power rule. You drop the power and you subtract 1 from the exponent. But there's an additional component which says we must also multiply the derivative of f of x. Or if we use prime notation, just to be, I know I've been talking to some of you guys and you kind of prefer the shorter way of writing it, which I've been talking about. If we wanted to know if we have a function to the k power and we want to know what is the derivative of all that by prime notation, well, again, you can use the power rule on this. That's the summary of the extended power rule. There's just an additional thing to remember, and that's exactly how I would recommend memorizing the chain rule. But basically, you drop the power and subtract 1 from the function. What's notably important is the interior of the power does not change when I apply the power rule. That remains exactly the same. I'm not taking the derivative of that. But what I must do is I must multiply by the derivative of the interior function, ddx of f of x, or again, f prime. That's a little messy looking, so I'll just rewrite it, f prime. And this is the essence of what we call the extended power rule. But it's really the same idea as the chain rule. So let's go ahead and practice applying this. So let's say I wanted to know what is the derivative of 4 minus x squared to the third power. Again, we could expand this all, but the point is that we don't need to because we could use the power rule in the extended fashion. So the gist of it is, again, I could think of, well, the inside here is f of x, and that is all raised to the third power. So the derivative of it, I'm going to use the normal power rule. Basically, all of that is to the third power. Well, I could drop the third power, keep the inside the same, and subtract 1 from that power. Essentially, I'm just using that power rule on the exterior exponent. So I drop it and subtract 1 from it. Now, the catch is that is all fine and that works, but we also need to multiply by the derivative of the inside. So, or by f prime in this case. So again, I could think of this as k f of x raised to the k minus 1, and that needs to be multiplied by the derivative of f or f prime. So basically, derivative of the inside, which is, well, the derivative of 4 would be 0, and the derivative of negative x squared would be negative 2x. And this would leave me with my derivative of this extended power function. It's not a power function, but it's something to a power. And as usual, we want to simplify this. Well, I have two components on the outside. 3 times negative 2x would be negative 6x, and then multiplied by 4 minus x squared. And I could multiply that all out, but a lot of times it's fine just to leave it in this sort of factored form, especially because the original function was presented in a factored or, exponential notation. So there we have it. And another thing that you might be wondering is, how do I know that this works? But again, it's another rule that's derived in much the same way as the product and quotient rules. It's even a little bit more complicated algebraically speaking, but you can trust these rules as being law. And I would always suggest looking at the proofs of these for yourselves. Actually, I don't even remember if our book goes into the proof of the chain rule, but at the end of the day, it's important to know the rules. I think understanding them is also important, but I'm trying to keep our lectures from getting too long, which they have been lately. Anyways, let's just do one more real fast, and then let's talk about the chain rule. So again, same deal. Here I treat the inside as f, and if I'm going to apply the chain, or technically this is the extended power rule, but it's really the same idea. The gist of it is you can take the derivative of the power part, drop the 5, and subtract 1. Keep the inside the same. And then the last step is I need to multiply by the derivative of the inside. So the inside here is x cubed plus 4. It's a polynomial, so I could just use normal power rule, derivative of x cubed is 3x squared. Derivative of 4x squared is plus 8x. Derivative of negative 11x is minus 11. And the derivative of 7 is 0. So differentiating all of the inside, I would have all this. Again, we could expand this all, clean it up. Let's just leave it at that because that gives us the gist of this. And really, it's like an algebraic simplification. Instead of having to go through an elaborate series of multiplication and then differentiation, it's a nice shortcut. And this rule doesn't just work for a function to a power. It actually works for any two functions composed together, and it is exactly the same rule. So let's go ahead and look at the chain rule, see how that is different. But what it says is if I want to take the derivative of f of g of x, aka one function within the other, and again, we can kind of think about this in the same way. We can think about f of x as the interior function, and the power x to the k is the exterior function. So this is really a composition of any function with a power function. And what it's saying is the power rule still works, you just have to multiply by the derivative of the inside. And that's exactly how the chain rule works too. It says that the derivative of a chain of functions is equal to f prime of g of x times g prime. Or in the simpler way of saying this is take the derivative of the exterior function, leave the inside alone, and multiply all that by the derivative of the inside. And that's exactly how this rule works. So if this rule makes sense to you, it is exactly the same with the chain rule, but it can be applied to any functions, not just powers. And notice we took the derivative of the... So what I think is important to focus on is what is inside and what is on the outside. Here, I have like my parentheses raised to the 5th power. That's kind of like the exterior function is the whole thing's to the power. So I'm taking the derivative of the outside first by power rule, and I keep the inside the same. That's exactly what this is. Take the f prime, leave the inside alone. And then the other thing I have to remember to do is then multiply by the derivative of the outside after, multiply that into the rest of the things. And that's actually the same as the chain rule. It works in every time. And sometimes you can think about it in the context of u substitution. So this could be helpful. Usually I don't like this approach myself, but I could think about this function as being u to the 5th power originally. And I could set u to being all of this stuff. I could then change this derivative to what is d to u, and then I would need to take, well, what is d dx after that? Or I'm not exactly writing this correctly. I would want to multiply this by du dx. And basically this alternate form is the Leibniz form of the chain rule, which it doesn't necessarily look the same if you're not used to looking at the difference in notation, which I know in our class we haven't talked a whole lot about the differences between prime notation and Leibniz notation, but notice what we get is the same exact thing. So I would think about this as y. So this is the same thing as dy du. I'm taking the derivative of this with respect to a change in variable after performing u substitution. And this would just leave me with 5u to the 4th. And then what I need to do is multiply by du dx, which is just the derivative of the inside. So basically that would represent this. And again, since u is the inside, this gives me exactly the same thing that I got here. I would get 5 inside to the 4th times the derivative of the inside with respect to x. And that's kind of what this means when I'm, in Leibniz notation. And, just to reiterate, I need to use the chain rule when I have a function within another function. So this video is getting a little bit long, and the next video we'll walk through some of the examples from the packet.